possibly spend an entire other day doing nothing but one ramp problem. So I want this quick. And if you can't do it, you have a problem you need to fix. So I'll put all that together real quick. You talk with whoever's there, but I am probably going to put one or two people in an uncomfortable position to explain what they did. So let's just say we give it a quick tap. So we've broken static friction and it's already sliding. So if you are not feeling skilled, frictionless. If you're feeling skilled, coefficient of friction of 0.25. But just know this will never be on our test, okay? It's gonna be this. So if you wanna know what we're doing. And I'm going to have to do a something in a day or so to check your abilities. So you know what that means, right? So you should probably expect that Friday. So give it a shot. There's nothing new here. If you don't know, then you have to assume it's a second law problem. It is possible that whatever numbers I just chose, it could be moving at a constant speed, right? So we don't know whether it's traveling at a constant or not. So under that circumstance, you choose second law. I asked you to find the acceleration though. Pretty good clue that it's a second law problem, correct? So start by just doing the obvious things. Free body diagram, there's gonna be a group of forces. I have no intention of doing the version of this problem without friction. But if you were doing the version without friction, you would have stopped here, right? But that's not what this problem is. There's still one more force. The frictional force has to be up the ramp because the object is traveling down the ramp. You were given the direction of motion. Don't assume you'll always be given that, but you were in this problem. We don't actually know if the object is speeding up or slowing down, and there's a pretty easy way to find out. But let's get to the point where we can find that. I'm going to do the problem without throwing in any numbers till the end. And it's important that you see why. But this is where you start. Any questions about this? If you did not get this answer, you should be hurriedly trying to make this picture. But note that I'm not going to stay here, and you should be working faster. I'm going to decide to make the positive x direction down the ramp. That is the direction I think the acceleration is. That's going to necessitate that the normal force is aligned with the positive y direction. That also places the angle theta here. Any questions about those choices? This is a ramp, this is not new, we've done this problem before. So I'm gonna take and break this up into components, mg cosine theta. And yes, I am thinking at this point you should be this quick at doing these things. Maybe not even have to draw the picture every time. So if you're not, go home and practice. Draw this out several times. Learn how to do this by straight rote memorization if you have to. But this is the speed. Net force in the x direction equals ma. Net force in the y direction equals 0. I'm choosing that on purpose. I aligned the x direction with the acceleration to purposely make the y direction equal to 0, which means normal force equals mg cosine theta. And mg sine theta minus friction equals ma. This is what Newton's laws provide for you. Any question about that?
A little over 6.
Hurriedly writing. Whatever it is friction, you couldn't do. Wherever you found that you were stopped, friction. Write it down. And
if
tell
you're not able
to
to get it in that amount of time,
you need to be at this
then you have
pace,
a problem.
This
You're
speed.
not at the level you need to be.
Friction equals mu times the normal force.
If you need this worked out, I'll work it out.
That's what's necessary here.
I saw a lot of right
It's on the
answers.
equation sheet. This is kinetic friction, so it's an equality. I'm going to do some substitution. Friction equals mu mg cosine theta. Right? And then one more substitution. Mg sine theta minus mu mg cosine theta equals ma. I subbed here, subbed there, and then put it in up there. The mass was irrelevant. This happens more often than you think. So although you were given the mass, you never needed it. And here's the important thing. The acceleration equals g sine theta minus mu g cosine theta. How do you know if it was speeding up or slowing down? It's all right here. The velocity was down the ramp, and we made down the ramp the positive direction. If this was negative, then it'd be slowing down, because the acceleration would be up the ramp. That's how we know. If this is positive, then it's speeding up, because the acceleration is down the ramp. Whether it's speeding up or slowing down depends on the velocity. But we knew the velocity was down the ramp, which is why we were able to tell whether this is speeding up or slowing down. Now, you plug the numbers in, you'll get your answer. That part's the least entertaining part, but you should probably realize that any block sliding down a ramp, this will be its acceleration. Any one of them. So, I mean, some of these things are things you could probably start to recognize, perhaps even remember. But every block sliding down a ramp will look like this. Back here, we know this has to be the part of the weight that's down the ramp. And we know friction is going to be mu times the normal force, and the normal force is still going to be mg cosine theta. You're not I assumed I told you guys same as last time. The next thing I should ask you to do, and I don't want to, but the next thing I should ask you to do is to consider a problem like we just did. And I'm going to tell you the parameters of the problem, but I'm not going to spend time working it out. I'll tell you the answer. And you should practice. This is for those of you who had difficulty just a minute ago. Let's chuck this box up the ramp at 4 meters per second. Let's stick with a 5 kilogram box and an angle of 20 degrees. How far up the ramp does it go before it stops? The answer is just under 1.5 meters. It's just under 1.5 meters. This problem isn't different than what you just did, right? It really isn't. And if you paid attention to what we just did, you could probably move pretty quickly through this problem. I don't want to offer too much time for this, but you should probably give it a quick shot, about 60 seconds or so, and see what you can kind of perform. Be careful. There is something different from the last problem, but not much. So I made up the ramp positive. Is that okay with all of you? Is this what you did? I mean, you can go reinventing the wheel here. So we can reuse all of those things. It's just that friction and mg sine theta both point down the ramp. They're both in the same direction. So I made them both negative. That's the only difference between what you just did and this example. But once you've done that, and you cancel out all the m's, this is a motion problem. With this being the acceleration, v naught being 4 meters per second, final velocity is 0, and you're looking for delta x. Right? This is just the next step of these problems, is to take this and turn it into a motion problem like we talked about earlier. I know I'm going fast, but do you understand why I don't want to spend all class period on an inclined plane problem? This is practice that you guys need if you're unable to do it at this kind of speed. And there's lots of practice in your homework, but this is the inclined plane problem. There's other versions of it, and there's other things we could talk about here. But ultimately, it comes down to you being able to realize the interplay between the normal force, the coefficient of friction, and the weight down the ramp. Does any Anybody need to see this more worked out? Can we try something new? Are you going to raise your hand? Are you thinking about raising your hand? I'm not talking to you, but I was talking to Gabby. She's the one all doing this thing. You weren't, so.
Isn't the acceleration going down?
Yeah.
Because it's slowing down the.
I believe it's slowing down the block, yes.
So wouldn't it make more sense to make the left, like going down the ramp a positive X?
It doesn't make any difference at all. If I make the left positive, correct? Then I would just make both of these positive, right? That would make this negative. It was not going to change my answers. Right? It's just going to change the positive or negative of my answers. I mean, look further down the road. And you're asking, so I'm just trying to provide you with perspective. You're going to use v squared minus v naught squared equals 2a delta x to solve this. Correct? Whether I make up the ramp or down the ramp positive or negative, this will be negative. Right? Because if I make up the ramp positive, then v naught's positive. If I make down the ramp positive, then this will be negative, but I'll square it, and that's still going to make the whole thing negative. Right? Because I'm still subtracting 0 minus that. Right? You following the argument so far?
A little?
Well, if it's a little, then I'm not going to bother. Gabby, what does this equal?
I didn't get it.
I'm waiting. And there's other people in the room, so I'll pick on another person. You work it. It's 10 times sine of 20 plus 0.25 times 10 cosine 20.
The coefficient of.
Oh, just the same as one as last time. Sorry.
Um,
Sorry. You guys could be forgiven for not having an answer then. So provide me one now. Sorry, I thought I said same kind of ramp as last time, but I must not have. It tells you how tired I am of doing inclined plane stuff. So Gabby's question is, doesn't it matter that we had downwards negative or downwards positive? Let's do the math, folks. If I make downwards negative, like I had it originally, this number's negative, correct?
yeah.
So 0 squared minus 4 squared equals 2 negative 5.76 times delta x. Okay? No, don't. You don't need your calculator for this. Look closely, okay? If this is going to be negative, has to be 0 minus anything, going to be a negative number, right? Now, this side then is negative. This side is 2 times a negative number, right? Will this be positive or negative?
It will be positive.
Has to be, right? Has to be. That means that the box went up the ramp because that's where positive is, right? Positive displacement. So you're concerned about the signs. So let's switch them. I'm making up the ramp negative and down the ramp positive. That will have the effect of making that number positive. It also has the effect of making this number negative, right?
Yes.
This is still negative. This is now positive. What has to be the sign of displacement?
Negative.
What direction is that? Up the ramp. Does it make a difference? No. Consistency makes a difference. Pick one and stick with it. That's what makes the difference. And a recollection that negative and positive is about direction still. We get it in our brains that it's not, but it's about direction. It's just telling you the direction of your answer. That good? Okay. No worries. There are forces that are proportional to velocity. We call these drag forces or air resistance. They can be proportional to the velocity. They can be proportional to the velocity squared. There's a variety of different kinds of forces out there. So far, all the forces we've been dealing with have been constants. They are the same under all circumstances, but they don't have to be. So in some circumstances, you will have forces that change as the object's velocity changes. This is a problem, especially when you consider that if those forces are unbalanced, then as the object accelerates, the forces that are acting on it are also changing. One of the simplest examples of this is just dropping something through the air. Something, say, light, and this is a lab we're going to do in about 2 weeks, a coffee filter. The thing about dropping a coffee filter is that A, you can change their mass really easily by just stacking them together. And B, the way they're shaped, they fall through the air slowly because they have a very high cross-section compared to their mass. So they don't fall at G, they fall much slower than G. And they reach something called terminal velocity. I want you to think about the forces acting on the coffee filter as it falls. First, we know that it's going to be experiencing a downward force due to gravity. By the way, this is example 4. And the inclined planes are example 3. So we're going to have a downward force due to gravity. This is a constant because generally the weight of an object as it falls doesn't change. And we're going to look at just one of the drag forces today, this one. This says that the drag force is proportional to the velocity, but in the opposite direction. So I think it's pretty clear that if you drop the coffee filter, it's going to fall with a velocity in this direction, which means the force of drag will act on it this way, right? This will be the force of drag. I'll put a little d there to differentiate it. Now, I need you to think about this a little bit because this is where it gets a little challenging. At t equals 0, the force of drag is 0, right? There's no velocity. If I drop it from rest, then at time 0, there is no drag. You ready? Follow that argument? An instant later, because it's an unbalanced force, I start getting a drag force. But for every instant that it falls, although the weight is staying the same, the drag force is going to be becoming bigger and bigger, but it doesn't keep getting bigger. It will eventually reach a point where it's balanced. Because at this moment, when the drag force equals the weight, the net force is 0. This is a force that changes over time, and it's based on the fact that the velocity is changing. These kinds of objects will reach something called terminal velocity. Terminal velocity is a term that refers to a situation in which an object that has a force that is proportional to the velocity reaches a state of net force equal to 0. All objects that fall through the atmosphere will eventually reach terminal velocity. And in fact, one of the first things I would expect you to be able to do is be able to say something like, what is the terminal velocity? You can figure it out. It has to be when mg minus kv equals 0. That has to be when it reaches terminal velocity. And by the way, it's not a big deal, you just solve for it. This is terminal velocity. Yeah?
What does the K stand for?
The K is a proportionality constant, and in most cases, K is let me back up. Let me say this in a thoughtful manner. In real life, K is a collection of things that has to do with the aerodynamics of the object and the viscosity of the fluid that you're falling through. So K would be something that would change if your object were shaped like a big square versus something that had like a nice, clean aerodynamic cross-section. So that's factors that go into K. Also, viscosity is the thickness of the fluid. So if you're dropping a BB through like molasses, well, that K would be different than dropping that same BB through water or through the air. So the viscosity of the liquid, the thickness of the liquid or fluid makes a difference. Calculating K actually is cumbersome and complex. So in this class, we just say all of those factors are just this number K. But the actual thing, yeah, if you look up the aerodynamic coefficient, which is one of the factors that goes into this, it's complicated. It has things like cross-sectional area play a role in it. So if something's very spread out cross-section wise, that would increase K. You get more force, like a sail provides a lot of force because it has a big cross-sectional area. But something that has less cross-sectional area will have less force. So K would go down for something that has a smaller cross-sectional area. I'm sure you've seen like videos of people who do skydiving. Well, when they spread themselves out, they are increasing K, which increases the drag force. It changes their terminal velocity. They're falling the whole time, but they can slow themselves down by increasing K, because K is in the denominator. That's what the parachute does. Parachute suddenly increases K by adding a lot of cross-sectional area all of a sudden, and that reduces how fast they're falling. Now, all of these things are predicated on the idea, though, that how fast this grows, like how fast you go from having no drag to having lots of drag, does depend on K. So you're right to ask what is K, but it has no more of a description than it's a proportionality constant that has all sorts of this stuff all wrapped up into it. Does that make sense? Now, here's the interesting thing. Although you as a skydiver can change your value for K by changing your cross-sectional area, once you understand that K is in this denominator, then you understand making those changes, how it affects everything else. Does that make sense? Okay. Somebody else had their hand up.
It was me, but you answered.
Okay. Now, the reason, we're not going to spend a lot of time studying this kind of problem, but there is something that you guys need to see. In problems that involve drag, we're going to be only looking at simple situations of drag where our problems are one-dimensional like this. Obviously, because they are complicated, we're not going to also complicate them by adding lots of geometry. So you'll notice this is a one-dimensional problem. I've just dropped this object through the atmosphere. These are harder to study because this is changing as the object accelerates. However, you learned something earlier in the year, and I want to reiterate it right now. You learned that acceleration is equal to the rate of change of velocity, and you learned that velocity is equal to the rate of change, velocity is equal to the rate of change of position. You learned that earlier this year. The reason I bring this problem up right now is to introduce you to a differential equation. And I'm introducing it because the most likely place you'll have to deal with differential equations will be on Newton's second law problems. There's one or two in your homework. They're just designed to have you set this up and do the following 3 activities. Activity number 1, create a net force equation. Not this one. Create the one in the middle here. One when it's still accelerating. So that'll be net force equals MA. I'm going to make downwards the positive direction, and I'll get mg minus kv equals ma. All of this, I feel, is something that's in your capabilities based on what we've done so far. So we have a force that is proportional to the velocity. If the object is falling through the atmosphere, I expect you could make a free body diagram based on what we've been talking about so far, and you could construct a Newton's second law equation. All reasonable things? Okay, that's the first activity. I would expect you to be able to come up with the middle, which is when it's falling but not at terminal velocity. I expect you to be able to derive the terminal velocity. by setting that same force equal to 0 and finding out how fast the object has to be traveling to be at terminal velocity. And then I'm going to expect one more thing. I'm going to expect that you could create a differential equation. All a differential equation is an equation that has a differential in it. You have two choices to either replace V or replace A, because you have a differential for both. I'm telling you right now, you replace it so that you have one variable in your equation. That means we replace A with the differential, so all of it's in terms of one variable. I expect to be able to do three things with these kinds of problems. Set up a Newton's second law relationship for when it's in the middle somewhere. Look at the situation when net force equals 0 and create a differential equation. If you're asked to create a differential equation, it's most likely going to be a Newton's second law problem. Most likely. 90% of the time it is. 10% of the time it's an energy equation, but 90% of the time it's Newton's second law. Some of you have completed a course in calculus. You should solve this. Solving this means V as a function of t. But most of you haven't completed a course in calculus, so I won't expect you to do that. But if you have completed a course in calculus, you should solve this. The process, we're all going to have to learn it, but I'm not about to add this to the burden of what we have right now. I am expecting you to do these three things. Everybody understands? There's two, I think there's two of these in your homework. I want you to practice, and I want you to try this out. Sometimes they'll have it like this, where the initial velocity is 0 and it's dropped. Sometimes they'll start it with some kind of starting velocity, like throwing it upwards into the air and asking about air resistance when it's been thrown upwards into the air. Each situation is a little bit different. Your job is to try and prepare this set of relationships, but I want these three things done. All right? So far, you've seen all the stuff that changes an object's velocity. But forces can cause things to change direction. We're not going to do anything where an object's speed and direction are changing at the same time. We'll pick one or the other for a long while. So all the stuff you've seen so far has allowed you to deal with velocity this way, right? Where velocity is changed based on an acceleration. Something is speeding up or something is slowing down. For the next few discussions, which will probably be today and Friday, we're going to talk about what happens when that force causes something to change direction. We're only going to look at a very narrow slice of this, and that narrow slice is centripetal motion. Centripetal, there's probably an I in there, motion. I think the I is here, but I don't know, don't care. Center pointing, that's what that means. Centripetal means center pointing. I'm careful to describe this in a very specific way, but we're talking about when a force applied to an object causes an object's direction to change. This can only happen if the force is perpendicular to the velocity. Did you really just pop your gum? Now, you can have a force that's at an angle to the velocity, but that would cause the object to speed up and turn at the same time. So I'm saying it like this. We're talking about centripetal motion. This object isn't changing speed, it's only changing direction. So kind of get an idea of an object that has a velocity in this direction. This is the direction of its velocity. And I apply a force this way. there's no part of the force that is in the direction of motion, either causing it to go faster or causing it to go slower. So this is going to cause the object's velocity to change to the left. Now that means that the object's path is going to veer. And a few moments later, the object is going to be over here with a velocity in this direction. Same size velocity, different direction velocity. Now, if your force were to remain this way, then the object wouldn't be traveling in a circle. The object would be a projectile. And we've studied projectiles before. This is what would happen if gravity is acting down on something and you throw something sideways, it just falls to the ground. If you want it to travel in a circle, then you have to keep changing the direction of the force to be perpendicular to the velocity. If you want something to travel in a circle, you have to keep changing the direction of the force so that it stays perpendicular to the velocity. So that a few moments later, the object continues its path, but the path is changing, makes it over here. The velocity is the same size, but now the force has changed direction again. If you'll notice, if the object wants to travel in a circular path, these forces have to keep changing direction. They point at the center of the circle. This is called a center-seeking force. That's where the word centripetal comes from. This is not a new force. There is no force that is a centripetal force. There is a force in nature that causes centripetal motion. That force would be called the centripetal force, but any number of things can cause a centripetal force. If you attach a cable to a ball and you swing the ball around your head on the cable's tension is a centripetal force. If it's a car on the road, what do you think causes the car to change direction? I know you'll say tires, but what force causes it? I don't think you'll be surprised when you hear it. I'm pretty sure most of you have driven a vehicle or at least seen it done. If you want to turn, something like that. The drive wheels, if yours is rear-wheel drive, still back here. If you have front-wheel drive, of course, your front wheels are doing it. But the reason the car changes direction, I know you think it's because the wheels have turned and the car is driving in that direction. But there's a force against those wheels, and that force is preventing the wheels from sliding. Right? It has to be friction that causes the car to turn. It's the fact that the wheels don't slide that makes the car turn. It's in this case, static friction that causes the car to turn. So in this case, static friction causes a centripetal force. When you swing the ball around your head, tension causes a centripetal force. What you need to put in your notes now is that for an object to travel in a circle, there must be an unbalanced force caused by one of the forces in nature. It's going to be on your list of forces. So it's going to be tension, normal force, frictional force. Something causes the object to travel in a circle. It is the unbalanced force that does so. The difference is that this acceleration is not a change in speed. So we give it a subscript. We put a little c here to say that it is a centripetal acceleration. All of the things you have been doing so far this year don't change. You will still say things like, Is there gravity acting on the object? Is the object in contact with some surface? Is there a string attached to the object? All of those things have to be there, but one of those forces has to point towards the center of the circle. What you're going to do different is this acceleration is based on the velocity and how quickly you want to make the turn. The centripetal acceleration is the ratio of your speed squared divided by the radius of curvature. This is different. This is a whole new thing. If you want to calculate a centripetal acceleration, it's the velocity squared divided by the radius of curvature. Now, there are some interesting limits here on how this works. And the problems associated with uniform circular motion can be complicated. I want you to know a few facts before the bell rings here. First, we're going to deal with situations in which the object's speed and the radius of curvature stay the same. That's the first thing we're going to do. We're going to make sure that this value isn't changing while the object is moving. Next, we're going to deal with basically small, simple, two-dimensional problems where there is an unbalanced force that has to cause this. The first one is going to be the easiest one, but we're out of time. So